So good morning. So let me first start by thanking the organizers for giving me this opportunity to present this work. So I'm going to speak about generating entanglement by quantum resetting. This is the work in collaboration with Satya, and I'm going to mainly speak about this work here, but I also wanted to mention this recent paper. So let me just start with the main statement. So the main statement is when we have non-zero quantum resetting, I'll explain these things in red here, together with non-zero interaction strength, then you can generate in a quantum Hamiltonian, you can generate entanglement in the non-equilibrium steady state, and this entanglement will be quantified by a non-zero concurrence. So I'll try to explain these words here, and this measure of entanglement can also be optimized by appropriately choosing two parameters, and the two parameters that are important are the resetting rate and some interaction strength. Okay, so this is sort of the main statement of the talk. So it's okay. So let me just start with some basic idea of quantum resetting. So that first appeared in this paper by Mukherjee, Sengupta, and Majumdar. And the idea is that when you have an initial condition with some density matrix, you have a unitary dynamics, and then this unitary dynamics is interrupted by stochastic resetting. So every now and then, you basically reset it to some target state. And then basically, this is another way of writing it, and that basically gives you some quantum version of a renewal equation given here. So this rho here is the time evolution of a density matrix of a quantum system in the absence of any resetting. And this R subscript here is in the presence of resetting. So this is basically the quantum renewal equation, and basically this equation almost always has a non-equilibrium steady state. If you take t go into infinity, this is basically Laplace transform of the unresetted density matrix. So that's fine. I'll just do it here. Yeah. So this is the important equation here. So you have your usual quantum evolution, rho of t, rho of tau, and then you basically get the density matrix in the presence of resetting. So now I'm going to mention some subtle points about quantum resetting, which is important for us. So one is the limit r goes to 0 and t goes to infinity does not commute. That is sort of easy to see here. If you take r goes to 0 first, you might not even have a steady state. So you have to take t goes to infinity and then take r goes to 0. And the second point here is that your density matrix without resetting may be a pure state. But then in the presence of resetting, you basically end up with a mixed state. So what quantum resetting does is basically it sort of mixes true quantum correlation with some classical mixedness. So question is, how do we separate this quantumness and this classical effect? So this is an interesting question which we have been thinking about. So that is the main point I wanted to make, that quantum resetting, that is resetting stochastically to a target state, eventually always gives you a mixed state. And you basically have a mixture of classical and quantum effects. So the three quantities that we consider are, we study the von Neumann entropy, which is not a very good measure for quantum entanglement because we have mixed states. But nonetheless, this is a piece which is quite useful as entries for other measures such as quantum discord and so on. And then we study fidelity, which basically says how close density matrices are to each other. And the most important quantity we study is this concurrence, basically which sort of, basically is a very good measure of quantum entanglement. So basically it basically says how easy or difficult it is to write the system as separable density matrices. So this is basically the three things that we study. So I've not spoken about the Hamiltonian yet, so now I'm going to describe the simple Hamiltonian that we have in mind. So think of a setup which is something like this. You have two qubits with some interaction J, and alpha is basically some renormalized interaction, and with some resetting rate R, which is again small r by this capital omega. So basically, imagine a simple system like this. and you prepare the system in some down-down state and let it evolve. So you let it evolve, and now and then you do quantum resetting to the down-down state. Okay, so that is the setup. So notice that suppose I did not have this interaction J at all. Imagine I have a bunch of uncoupled qubits and I simultaneously reset it to a down-down state. That already dynamically generates correlations. Okay, and that has been sort of addressed in this paper. But then, interestingly, it really does not quantum entangle the system. Okay, so there is a dynamically generated correlation in the quantum system, but there is no quantum entanglement. For quantum entanglement, we need some interaction J. Okay, and the point is the concurrence that I was describing before brings out this physics. So this is the setup, and now you can basically derive everything in terms of capital R and capital alpha. So von Neumann entropy and fidelity, and basically you can see that many of these expressions sort of make sense because you can see that, for example, if you take R to infinity, you keep on resetting it to a down-down state, then the fidelity is close to 1 because you reset it so much that it just remains close to the down-down state. Okay, so you can basically calculate this von Neumann entropy as a function of interaction strength alpha, and we notice a nice, very interesting minima and the inflection point. And then you can also calculate time dynamics in the presence of resetting, which is given here for different resetting rates. And this is a quantity fidelity in the R alpha plane. So basically R alpha is the important plane here. So now let me end with the important quantity, the concurrence. So concurrence, so I have 2 qubits. So let me again remind you the setup. I have 2 qubits. I prepare it in some down-down state and I let it evolve, and I do stochastic resetting. And now the question is, how quantum entangled can it get? And the concurrence is basically maximum of 0 and this number, and this number is essentially these are just eigenvalues of this R matrix, where R matrix entries are given by these density matrices. But the important point is what concurrence says is if the density matrix of a full system can be written as convex sum of separable density matrices, then the concurrence is 0. So let me just write it here. So if the density matrix can be just written as some AI rho I system A times rho I system B, if a density matrix can be written as a convex sum of these separable density matrices, then the concurrence is 0. But if you calculate something like von Neumann entropy, entanglement entropy, you might get some non-trivial von Neumann entropy, but still there is no quantum entanglement. So here you see that one of our main results is if you fix the interaction strength as a function of resetting rate, we see an optimal resetting rate. So there's an optimal resetting which enhances quantum entanglement in your quantum system, which is characterized by this concurrence. And similarly, if you fix the resetting rate and tune alpha, there's an optimal alpha where the quantum entanglement is maximum. So just by having too much alpha, alpha is the interaction strength, doesn't guarantee large quantum entanglement. And then you see this in this color plot. So basically, there is evidence of optimal resetting and optimal interaction strength to get maximal quantum entanglement. So I just wanted to end by saying that okay, so that's fine. So let me just go to the outlook, not the conclusion. So we would like to extend these studies to larger systems and sort of understand quantum entanglement and how it changes with system size, where we need good measures of quantum entanglement for mixed density matrices. And then we also want to see if there is a transition in this entanglement when you change R, when you increase R, which is similar in philosophy to measurement-induced phase transition. Thank you.
Any questions? So in principle, like each individual trajectory is for a pure state, right? When you average, you get a mixed state. But isn't it like, because you start with a
Right, right.
pure state and
Yeah.
you evolve it
So each
unitarily?
individual trajectory is a pure state,
Yeah, so
and
you
when
could-
you average it, it's
then
a
you
mixed
get a
state.
dense mix. So in principle, you could compute the entanglement for each trajectory and then do an average, right? I
Yeah,
don't know if that might give something.
So that will give you the correct von Neumann entanglement entropy, but that in the context of quantum resetting, it's not very clear how to do. If you use the renewal equation right away, then you lose that information.
Yeah, then of course you lose.
Yeah. So if you do individual trajectories, you should be able to get the actual von Neumann entanglement entropy. So we have not done that, but it's yeah.
Because that's what like people doing MIPS and all, that's they
Exactly,
look at
exactly.
individual trajectory.
Exactly, but in the quantum resetting thing, it's not clear how to do that. Yeah.
So, yeah.
Modeling for two sites, isn't that what you're looking at?
Yeah, so the thing is, if you have two qubits and you do the transverse field Ising model,
Yeah, but it has also a phase transition, right? Transverse field Ising model also has a phase transition of its own.
sorry, if it is?
The transverse field Ising model also has a phase transition of its own.
Yeah.
Does that play any role here?
So here we are just looking at two qubits.
Yeah.
Okay, so the thing is that the reason we are looking only at two qubits is because you can almost analytically compute the concurrence, because the definition of concurrence for multiple qubits is very complicated. So we are just studying two qubits.
So I'm trying to understand where are you in the, so although you have just two sites, if there's a phase transitions, and where are you in the paramagnetic phase or ferromagnetic phase?
No.
This is just two sites.
Yeah, just two sides, J greater than 0. So
Yeah, I understand. But later on, when you said you want to increase it to system sizes,
Yeah.
so then it will have its own phase transition also.
Yeah. So we don't really know. So we have not done that yet. So that's our goal, to actually study the many body system. But there the problem is not just, the difficulty is not just in scaling up the system. The difficulty is in trying to find the right measure of quantum entanglement, because in this setup, we always have mixed states by definition. So the point is that if you have a many body system, but it's in a pure state, then concurrence, the expression for concurrence is actually simple. It's just square root of 2 into 1 minus trace of partial rho square or something. But the point is that the difficulty is also in finding the right quantity to calculate. So that is the...
Sorry, I just have a comment. I mean, the phase transition that you're talking about presumably is the ground state phase transition. This thing is so far out of equilibrium, I don't understand why is that relevant.
No, I don't know. I'm just curious about the...
I think that phase transition, I mean, this entire protocol, even if you do it for a big system, is completely oblivious to the ground state phase transition.
Yeah.
Let us thank the speaker.